Welcome to lecture 19. In this lecture, we're going to carry on with doing magnetic fields around a current carrying wire, and we'll look at some examples and some different geometries. In this example, we have two current carrying wires. The upper wire is carrying current into the page. The lower wire is carrying current that flows out of the page. The wires are separated by 10 centimeters, and we'd like to find the total magnetic field at point P. So what we're going to have to do here is a vector addition. We're going to have to find the magnetic field due to the upper wire, find the field due to the lower wire. We'll find the direction using the right-hand rule. We'll find the magnitude using the equation, and then we'll do the vector sum of those two fields. So let's work on first finding the magnetic field due to the upper wire. I'm going to say that the current flowing in the upper wire is I1, so our top wire is wire 1. So I've got a video here where I take you through drawing that first magnetic field. Let's try and find the magnetic field around a current carrying wire. See in my picture here, I have a little X in a circle. That tells me that my wire is going up and down perpendicular to the page, and the current flow is away from us into the page. So something like this. We know that magnetic fields make big circles around a wire. So if I want to find the magnetic field at point P, I draw a big circle around this wire. The wire is at the center, and my circle itself has to cut through point P. I'm going to draw a big circle. You don't have to get it exactly perfect, but try and get it a little bit close. So this represents the magnetic field around our wire up here. I'll call this wire 1. To get the orientation of the field, you apply your right-hand rule. Your thumb goes with your current, so into the page. And then your magnetic field at any point is a tangent to the circle with the orientation given by the right-hand rule. So it comes down around clockwise. Exactly at point P, it's going to be a tangent to this circle. If you struggle a little bit with drawing a tangent, what you can do is draw the radius of the circle from the wire to point P. And then we know a tangent to the circle would be perpendicular to this radius. So you can just draw a line. Again, we're not doing this graphically, so it doesn't have to be perfect. You just want to get it kind of close so you get a good picture of what's going on. So there's the magnetic field at point P due to wire 1. We see it goes down and left because our fingers point down and left. So hopefully that makes it clear about finding the direction of B1. I'm going to draw it on this diagram here. So there's our B1. It is a vector, so it has a direction and a magnitude. Let's find the magnitude of that vector first. So the magnitude of vector B1 is mu naught times I1 over 2 pi times R1. Mu naught is our constant. Mu naught is 4 pi times 10 to the minus 7 Teslas times meters over amps. R1 is your distance from wire 1 to our point. So from here to here is R1. You might notice that R1 is the hypotenuse of a right angle triangle. So our horizontal length is 10 centimeters, 0.10 meters. Our vertical length is 5 centimeters, 0.05 meters. So our distance R1 is the square root of 10 centimeters squared plus 5 centimeters squared to give us 0.112 meters or 11.2 centimeters. So I'll put in that my current I1, that's given in the problem as 1.25 amps. Put in that my R1 is 0.112 meters, and I get the magnitude of my magnetic field at point P, B1, is 2.23 times 10 to the minus 6 Teslas. Magnetic field is a vector, so it has a direction, so I'm going to need to break this into components. I'm going to do that on the next slide. Let's work on breaking B1 into its components. If you're a little bit rusty with this, you might want to take your time going through this slide. If you're okay with vectors and components, then by all means you can skip through it. So our vector B1 has an x and y component. The y component points down, there's B1y, and the x component points left, there's B1x. Let's get those guys labeled. And to find those components, we're going to need to find an angle. I'll label my x and y coordinate system. So I'm going to call my angle right here theta 1. I see that tan theta is going to be 5 centimeters divided by 10 centimeters. So theta 1 is the inverse tan of 5 centimeters over 10 centimeters. Put that through the calculator, you should get 26.6 degrees. If we look at our geometry, the geometry can be a little bit tricky here. Theta 1 is between the horizontal and R1. And then we have a right angle between the radius and the tangent, B1. So that means our angle in right here is 90 minus theta 1. So this angle right here is 63.4 degrees. And then we have another right angle between B1x and B1y. That means this angle is also theta 1, 26.6. Okay, so we see that our B1y is adjacent to our angle, our B1x is opposite our angle. So now we can find our components. B1x points left, so it's negative. B1y points down, so it's also negative. So B1x equals minus B1 sine theta 1. I'll put in my B1 is 2.23 times 10 to the minus 6 Teslas. I'll put in my theta 1 is 26.6 degrees. And I get my B1x to be minus 9.99 times 10 to the minus 7 Teslas. My B1y points down, so it's negative. B1 times cosine theta 1. Put in my values, and I get minus 1.99 times 10 to the minus 6 Teslas. Okay, so there's the magnetic field due to wire 1, and that's all broken into components now. Next, we'll do the same deal for wire 2. Then we'll be able to do a vector sum to find the total magnetic field. So we'll take our wire 2 to be the one on the bottom. That's carrying current I2. Let's use our right-hand rule, and let's find the direction of the magnetic field at point P due to wire 2. Similar to how we found the magnetic field around wire 1, we can find the magnetic field around wire 2. This wire is represented by a little dot inside of a circle. That's telling us that our wire is perpendicular to our page and the current is coming up towards us. So our magnetic field makes big circles around the wire. We want those big circles to cut through point P. Looks something like this. Again, it's hard to get it very close, so a little bit like this. Trace that out in red. To get the orientation of the circle, we know that it comes up and around. So we put our thumb with the current, which comes out of the page, and our fingers are coming up and around. So the orientation is about like this. To get our magnetic field at point P, we know it's going to be a tangent to that circle. To draw your tangent, it may help to draw the radius of the circle. And then our magnetic field would be a tangent to that radius. So I didn't do exactly perfect with my circle. There's my B1. My circle maybe should have been a little bit more like this. It's a little bit hard to draw freehand. So there's your B1. B2, because it comes from wire 2. So now we have the two magnetic fields, and once you have the directions, you can use your equation to find the magnitudes, and then you can do a vector addition. So let's get a drawing of B2 done on our page here. So B2 goes up and to the left using our right-hand rule. Hopefully that was fairly clear there. Let's find the magnitude of our magnetic field B2. So the magnitude is going to be mu naught times I2 over 2 pi R2. So R2 is from the wire to the point. There's R2. So that goes up by a vertical distance of 5 centimeters, and it goes to the right horizontal distance of 10 centimeters. So the magnitude of R2 is the same as the magnitude of R1, which is 11.2 centimeters. And the wire 2 carries the same current as wire 1 did, 1.25 amps. So I can put that in my equation, and I find that the magnitude of magnetic field B2 is the same as the magnitude of the magnetic field of wire 1. And that makes sense because point P is equidistant from both of them, and it carries the same amount of current. On the next slide, we'll find the components of B2. Let's get our components now of vector B2. B2y points straight up. So that one's going to be positive. B2x points to the left, so that's going to be negative. We're going to need an angle. I'll call my angle right here theta 2. That angle is the same as this angle, theta 2. By the symmetry of the problem, theta 2 has to be the same as theta 1. So theta 2 is the inverse tan of 5 centimeters over 10 centimeters, the legs of that triangle, 26.6 degrees. Okay, so if this angle is theta 2, then this angle needs to be 65.4 degrees. And this angle also needs to be theta 2. Our B2x is opposite our angle, our B2y is adjacent. So B2x is minus B2 sine theta 2. That's equal to minus 9.99 times 10 to the minus 7 teslas. B2y is plus B2 cos theta 2, plus because it points up. So plus 1.99 times 10 to the minus 6 teslas. Next, we'll put it all together and find our vector sum. Our net magnetic field now is the vector sum of B1 and B2. So we can add up the x components to get our total x. When you add up those two x components, you get minus 2.00 times 10 to the minus 6 teslas. When you add up the y components, you can probably see that they sum up to be 0. They're equal and opposite, so they go to 0. So our total magnetic field vector then is minus 2 times 10 to the minus 6 teslas in the x direction, or I hat. So when you're doing these magnetic field problems, you have to find the magnetic field due to each wire. In general, you'll need to find the components, and then you'll need to do a vector sum.